So, in the spirit of getting you guys prepared for the reverse engineering report, remember, we are expecting for the buret stopcock combination for you guys to generate for us 3 fluid mechanics analyses, 3 dynamics analyses, 3 failure type analyses, and then 3 analyses that are sort of DML, mechanics of materials type analyses. And so I wanted to give you guys an example of another one, which is kind of a mechanics of materials, but also a Mech 1 type analysis, which is to determine the pressure at which the seals on the stopcock will start to leak. So here's my stopcock. I do not have the buret that goes with it. I was playing with the buret, trying to figure out how much I could bend it before it would break, and I discovered how much I can bend it before it would break, and it broke. So I don't have a buret now. I've got another one that's coming to me in the mail, but I don't have one. So all we've got is the stopcock, and you'll notice that the stopcock has got 3 seals, right? 1, 2, and then there's one that would be right there, but I pulled it off. But there it is. It's an O-ring, and it sits right there in that groove. And the buret is basically a hollow tube, a hollow acrylic tube that slides over those 3 O-rings and creates a seal that once you fill up the buret will not leak, right? The fluid won't leak out. And that's important. If you guys remember the video that I showed last time that described the function of a buret stopcock combination, you want to really precisely control the amount of liquid that's leaving the buret, traveling through the stopcock and entering into the Erlenmeyer flask as you're doing your acid-base titration. And so if you have fluid leaking past those O-rings, the potential is that the fluid would run down the stopcock in an uncontrolled way, go into the Erlenmeyer flask and mess up your titration. So it's definitely a failure mode if you run into a situation where you filled the buret so high or with a fluid that is so dense that the hydrostatic pressure is such that it overcomes the ability of these seals to prevent the leak. So that's a failure mode analysis that you guys can do for your reverse engineering report. So that's my plan today, is to at least begin the derivation to show you how to do that. It is likely we will not get to the end of the derivation, as I've discovered the hard way in the first 2 sections of class today. So what I will do is, again, complete those derivations on Wednesday at 9:35 and 11:45. So if you're available at those times, you can come to those class sessions. If you're not available at those times, I'm just going to make an asynchronous video that starts basically where we stop off, and I'll post that up on Canvas so that you guys can see the end of the derivation asynchronously. But either way, I'll make sure that you guys get what you need to get to the end. Okay, so let's just jump right into this. So our goal, let me move this out of the way. Our goal here is to, let's see, goal. So the goal of a seal, for a seal, is to eliminate unwanted fluid flow between 2 of your parts. So the goal for a seal is to eliminate fluid flow, I should say unwanted fluid flow between parts of an assembly. Okay, so how does a seal do that? Well, there are 2 different types of seals that we have to worry about. So 2 seal types. The first is called a static seal. Static, of course, means that it's not moving. And so an example of that is our stopcock buret seal is static. And then there's a second type, which is a dynamic seal. And dynamic seals are seals that move, that slide along. And so an example of that is a syringe. And it just so happens that I have a syringe here. This was the reverse engineering report artifact from the summer. and from fall 2019. And so I can demonstrate for you briefly what a dynamic seal looks like. So the way that a syringe works is that you put your medical fluid in the barrel here. So you suck up the fluid, and then you push on the syringe and you push the fluid out, and the fluid comes out of this little hole on the top, and you inject somebody with it, or you push fluid along a line of some kind, a tube of some kind, to get it where you want. If you didn't have a seal, which is right here, this black silicone seal, what would end up happening when you push the plunger down is that the fluid would just shoot out the back, right? Because there's nothing. The fluid would like to take the path of least resistance, and so if that seal's not there, it's not going to go into the pressurized line that you've got connected to the syringe. It's going to squirt out the back, and that's not good, because you want to control where the fluid goes with the syringe. And so the syringe has got in the plunger these three kind of O-ring like features. So there's one here, there's one here. Let me make this a little bit closer. There's one here, there's one here, and then there's one here. And so those are essentially O-rings that prevent the fluid from leaking past as the syringe is moving. But this, of course, is a dynamic seal, because the seal itself is moving with respect to the static barrel wall of the syringe. And so that's more of an example than our case, which is the buret stopcock, in which everything is static. Once I put the buret over the stopcock, nothing moves with respect to anything else. And so we've got a static seal in our case. Okay, so we've got the two types of seals talked about. How are seals made? How are they formed? Well, at least for our purposes, it's an O-ring, and this is an O-ring right here. So O-rings make seals. And an O-ring is a torus-shaped typically silicone rubber ring, although they can be made out of other things, but usually silicone rubber. Silicone rubber ring that deforms under pressure to create a sealing surface. Deforms under pressure to create a sealing surface. Okay, so let me switch to my next piece of paper, because I'm out of room here. Everyone have what they want from this page? Can I move on?
Yep.
Okay, cool. All right. So we'll start with just a basic model. So this isn't like a free body diagram or anything. It's more of just a conceptual model to get you to start thinking about how an O-ring works. And so the way that our O-rings work is we have a surface which is fixed, which I'll call surface 1. For us, this surface is the stopcock outer diameter. So for our purposes, it's this outer surface here of the stopcock where the O-ring is sitting. If you think about one of these O-rings and you look at it from the side, you slice the O-ring and you look at it, it's a toroid. So if I slice it open, it's the shape of a circle. So if I look at it sideways, I just get a circle, and let me hatch it to show you that it's solid. And this is our undeformed O-ring. And one thing that I will say very quickly, because it's caused confusion in the other two sections, is if you look very closely at the buret, you can see there's 3 O-ring like grooves, right? So there's a groove right here that contains the O-ring that I removed, just so that I had something to show. So normally when you design an O-ring, you put it in one of these grooves that's called a gland. And what the gland does is it has 2 functions. So one is it prevents the O-ring from like sliding up and down on the surface. And then the other thing that it does is, and I'll show you this in a second, when you compress the O-ring and deform it, if there's no gland there, the O-ring just sort of spreads out as much as it wants to in the axial direction of the stopcock, right? So the O-ring will just sort of spread out in that direction. The walls of the gland prevent that spreading process from happening. And so what ends up then occurring, if you think about Poisson's ratio, if you've got a force that you're using to compress the O-ring from above and below, it starts to spread out, and then it's prevented from spreading out any further. All of a sudden, the force that's required to get the O-ring to deform goes way up, because now the O-ring is sort of sitting in this groove and it can't spread out naturally the way that it wants to. And so these glands, again, prevent the O-ring from slipping, but also increase the sealing force by preventing the O-ring from just deforming all the way. And so even though I'm modeling an O-ring just sitting on a flat surface, really the O-rings sit in these glands that increase the pressure. So what I'm doing here is effectively a bounding calculation, right? So in engineering, if you can't do the full-blown calculation, the next best thing is to come up with like an upper bound or a lower bound, and then decide whether or not your solution, where it falls with respect to those bounds. And so the argument goes that if I do not have the O-ring in a gland, if I just have it sitting on a flat surface, I'm going to calculate a pressure required, or the pressure that the O-ring produces as it makes a seal. If the gland is not there, that pressure is a lower bound, right? If I put the gland in place, then the O-ring will actually be more difficult to deform, and the pressure that it produces will go up. And so the pressure that I get from this calculation is going to be a lower bound on the leak pressure for an O-ring sitting in a gland, because I've removed the gland. So that's my simplifying assumption to make the math doable. And interestingly, I actually went through the math. I calculated a seal pressure, and then I went to the Parker O-ring handbook, and I determined what the actual sealing pressure is for this particular O-ring in a gland, in a properly designed gland. And lo and behold, it's about 10 or 15% higher in the gland than it is just sitting on a flat surface. And so my lower bound approximation actually makes sense. So because I get close to the right answer, but not quite. So again, this is a lower bound approximation on the real answer if we have the O-ring sitting in a gland. Okay, so any questions or trouble with that? Nope, so far so good. Okay, so now I'm going to bring my buret into play. So I've still got surface one, which again is my stopcock. I've got a fly buzzing around here. And I'm now going to add the buret. So I'm gonna take the buret and I'm gonna slide it over, right? The buret is just a hollow cylinder. So I'm gonna slide it over these three O-rings and create what's effectively a second surface. So this is gonna be surface two. It's also, of course, fixed because it's part of the buret. So this is now the buret inner diameter. Whoops. Buret inner diameter is surface two. Surface one is still the stopcock outer diameter. And what happens in between is that the O-ring deforms, right? It deforms from that circular cross section into more of like a flattened oval. And this, by the way, is what I was talking about with the gland, right? If I do not have the gland there, the O-ring can just spread out as much as it wants to. If I have the gland there, the gland would stop the spreading of this O-ring and would induce then a higher reaction force, which would increase the seal pressure. But for our purposes, for just a simple analysis, we'll just let the O-ring deform as much as it wants to. So this is now my deformed O-ring. Okay, so how do I go from sort of this conceptual idea of how the O-ring functions into something that's going to tell me what the pressure is between the O-ring and the surface, so that I can determine what the leak pressure is for the buret when it's put over the stopcock? Well, I'm going to go all the way back to Hooke's law, so all the way back to physics, recognizing that the O-ring is squishy. And squishy is a very technical term, so I'm going to put it in quotes. Squishy. So I want to model it using Hooke's law. Which is just basically to assume it acts like a spring. Okay, so I'm going to draw first to sort of get you in the mindset of this spring analogy. First, I'm going to draw again my uncompressed O-ring. And I'm going to make an analogy between this uncompressed O-ring and an uncompressed spring. So here is my uncompressed spring. And when I compress the spring, I need to know what the spring's resting location was, right? I need to know where z equals 0 is. So I set a datum here. And when I compress the spring, it's going to look like that. So here's my compressed spring. And to get the spring to compress, I had to put some force on it. So that's Fn, N is for normal force. And the amount of compression that I got is this distance d from the rest location to the compressed location of the top of the spring. And so by analogy, I'm going to just now draw my uncompressed O-ring, and I'm going to, my now compressed O-ring, and I'm going to draw it, more or less the same way, right? So it's squished, sort of at the same level of this spring. And that is, just to be clear, compressed O-ring. And to get the O-ring to compress, I had to induce or put a force on it of F sub n, and the O-ring compressed by a distance d, right? So it's an exact analogy from the O-ring to the spring, compressing the spring and getting back to the compressed O-ring. Okay, so any questions about that analogy?
Quick question on the view of this O-ring. So the circle, because I know the O-ring is basically like a donut shape, really, but I'm just trying to visualize what view we're looking at the O-ring from.
Yeah, so I here, maybe let's see if I can draw it. So the O-ring is kind of like a donut shape, right? It's like a toroid. And so what we are looking at is a circular cross section. So like that cross section of the donut.
That makes sense. Thank you.
Okay. Yep. No problem. Other questions while we're here? Nope. Okay. Great. All right. So now we've got kind of this basic model. We've got our spring analogy, and so now I want to make this more formal. And so let's start with a free body diagram. So we've got free body diagram, and I'm going to just do a free body diagram on the compressed O-ring. So compressed O-ring. Okay. And the compressed O-ring is just a, sort of flattened oval. So it's going to look like this. And to kind of put things in context, right, I'm looking at the cross section, and I want a coordinate system that kind of aligns with my stopcock here. And so a coordinate system that kind of makes sense is if this, let's put it over here. If this is the z direction, that makes this guy the r direction, and then like around is the theta direction. So theta goes this way, theta direction. Okay, so that's my coordinate system, and the mass of this thing, right, the mg, is actually acting in the z direction, right? So if I've got this thing sort of, sitting this way, gravity is going to pull down, and it's going to pull down like through this compressed cross section. So it's actually going to pull like in that direction. So that's mg. And then I've got the surface on the bottom, which is going to be imposing a force upwards. So we're going to call that F1. So that's now the stopcock outer diameter pushing upwards on the compressed O-ring. And then I'm going to have F2, which is going to be the buret inner diameter pushing down from the outside on the top of the O-ring to give me effectively this free body diagram. Now, I also have, I'll draw it in here just for completeness. I also have very, very small but non-zero friction forces that are preventing the O-ring from slipping. And so if I do my sum of forces in the z direction, I've got z pointing to my right. So it's going to be mg is positive, and then it's going to be the friction force is negative, and because all this is static, that goes to 0. And then in the r direction, at least for this particular cross section of O-ring, I'm going to have let's see, F1 is going to be up, and F2 is going to be down, and that's going to equal 0. And so effectively what I end up with is that F1 is equal to F2, and mg is just equal to the friction force. And I'm not going to worry about what's happening in the z direction, because I know that in reality, my O-ring is sitting inside one of these glands, and so it's not going anywhere. Even if it started to slip as a result of its own weight, the friction force and then the reaction force from the gland would stop it from moving. So I'm gonna kind of forget about this, and I'm gonna focus on this because that's where all the action is, at least with respect to the seal. So let me pause there. Can I answer any questions about how I built up the free body diagram? Good to go? Okay. So let's move on from the free body diagram then to how we get a seal to actually, how we get it to actually seal. So what's going on is that I've got these two surfaces. You guys are going to get sick of seeing me draw this over and over again. I've got these two surfaces, and I've got this O-ring, this compressed, squished O-ring, kind of sitting between those two surfaces. So again, the O-ring is solid and compressed. On the side where I've poured the liquid in, I'm going to have, we'll call it pH for high pressure. So that's the hydrostatic pressure of the titration fluid that I poured into the buret. And then PL, that's low pressure. That's effectively just atmospheric pressure. That's the air pressure, on the bottom side. What I need to figure out then is what's the pressure sort of in this space that's between the O-ring and the buret, and the O-ring and the stopcock. So the high pressure here, looks like this. It's sort of these big lines, and then the pressure here is kind of these smaller lines. And you guys know, I hope you know or remember from fluids that if you have fluid at high pressure and you present it with the opportunity to move into low pressure, it's just going to go, right? It's going to go wherever you give it the chance to move into low pressure. And so this high pressure fluid is constantly trying to sneak past this barrier to get to the low pressure region. And so to prevent that from happening, we need to make sure that the pressure in this area between the seal and the surfaces is higher than the pressure difference between pH and PL. Provided we can keep that pressure higher than pH minus PL, we're golden. We won't have any leaks. So what is that pressure kind of in this space between the seal, the buret, and the stopcock? Well, we know from the free body diagram that it's effectively just two forces pushing on the O-ring from those surfaces, and I know that pressure goes as force over area, and so what I really need here is a pressure equal to a force over an area. Oops, that should be a force over an area, and the same thing up here, right? Pressure is equal to force over area, and provided the pressure that comes from the deformation and elasticity of the O-ring is greater than pH minus PL, then I've got a good seal, right? Because the fluid will not feel compelled to kind of slip through this region if that region experiences higher pressure than pH minus PL. So that's my condition for sealing. Which leads me then to need to figure out what this P is. And to figure out what this P is, I need to figure out what the force is, and I need to figure out what that area is. And so the easier thing to start with is the area. And so what I'll do is draw kind of another version of this. Like I said, you guys are going to get sick of seeing this after a little while. Another version of this that starts to kind of tease out what that area is going to be. So here is my compressed O-ring again. Not drawn particularly well. Okay, here's my compressed O-ring. And here is the geometric center of that O-ring, and here, and then again up here and up here. Those are the places where the O-ring is in good, oh, there we go, where the O-ring is in good contact with the surrounding surfaces. And so I am going to, just for my own sanity, start like assigning variables to important geometries. And because I know where I'm going, because I've solved this already, I'm going to call the distance between the center of the O-ring and the edge where it stops touching the surface as A. And so I'm going to have two of these lowercase a's. And if I've got two of the lowercase a's, and I know the overall circumference of the O-ring, because if I draw just again half of a toroid, so here's the O-ring again, just cut in half. So this, by the way, is the cross section that we're looking at here. And I've got sort of two axes that I need to worry about. One is the center line of the overall toroid, right? So if I look at the O-ring, this center line that I've drawn just is a line that goes right through the geometric center of the O-ring like that. And then there's another center line, which is the axis that's central to the cylindrical shape of the O-ring. So that's the dotted line there is that one. And I'm going to define this dimension, which is basically the radius from the center line of the O-ring to the center line of the major axis that runs through the O-ring, as capital R. So that's going to be capital R, which is a radius. The overall O-ring circumference, I'll call L. But I know that L is just equal to 2 pi capital R, right? So that's just from geometry. And so now I have everything that I need to express the area, right? Because remember, we're going for the area because we want to get to the pressure, to express the area in terms of variables that I can at least define, if not eventually measure. And so my contact area then, which we'll call capital A, is equal to 2AL, right? And so the way to think about this is it's just a rectangle, right? So it's a rectangle that has a width of L, it has a width of 2A and a length of L, right? The circumference all the way around. So that gives us our area, but then we know that L is just 2 pi R. So this is just, let's see, 2A multiplied by 2 pi R. And that gets us to 4 pi A R, right? So that's now our expression for the contact area. Okay, so let me write this pressure again. So pressure P is now equal to the force either acting on the top or the bottom. They're the same force, so I only have to calculate one. So I'm going to call this F1 comma 2, right, which means that I can calculate either one. It doesn't matter. The pressure is the same either way. And then I'm going to divide that by the area, and that area is 4 pi A capital R. Okay, so this is the pressure to hold a seal. So I'm just going to take this condition for sealing, and I'm effectively going to rewrite it. And I'm just going to say that pH minus PL has to be less than F1 or 2 over 4 pi AR. And that's now my new condition for sealing. Okay. So far, so good. Okay. We've got a few minutes left, so I'll move on to the next concept. As I said, I'm not going to have enough time to get all the way through this, but I will make an asynchronous video for you guys, or you can attend the 9:35 or the 11:45 a.m. sessions on Wednesday if you're available, and I'll finish the derivation live there. But we've got 3 more minutes, so let's just do the next little section of it here, which is actually really cool. We need to figure out what this A is, right? This contact area, which shows up here. And so what's A? I can get at A by effectively cheating, right? So physicists follow the rules and engineers cheat to win. And so we're going to borrow something from physics, but we're gonna cheat. So we're going to use Hertzian contact, which is the concept from physics. And the way that I'm going to derive this is I'm going to start with 2 cylinders. I need to draw that bigger. 2 cylinders that are in contact along just a single line. So here's one cylinder. It runs off kind of in this direction. Ooh, do better. Okay. It runs off in this direction, and it ends there. And then I have the bottom cylinder, which is slightly bigger, that runs off and it ends there. And the length of contact between the top cylinder and the bottom cylinder, that's just the length of these cylinders, which is L. And hopefully you can see where I'm going with this. That L, by the way, corresponds to this lowercase l that I had written before, right? So the L here is the circumference. If I just cut, right, just take one of these O-rings and cut it and unfurl it, I get a straight cylinder. So like the cross-sectional areas that we've been talking about, it's just literally this cross-sectional area down here. Okay, so the radius of the bigger cylinder is R2, and the radius of the smaller cylinder from the center is R1. And there's a line of contact between them, so contact line. And if I'm in a situation where I'm not compressing, if I'm not pushing one cylinder against the other, this is just, it's a line that connects them, right? It's a two-dimensional or one-dimensional line. But if I start to compress the cylinders to push them together, I end up getting a Hertzian connection, a Hertzian contact, which is a rectangular shape, right? So the equation of a rectangle. And the pressure that's in that space, that contact space between the smaller cylinder and the bigger cylinder, is pressure, and it's equal to a modified Young's modulus multiplied by the force that I'm using to do the compression, divided by pi L, and then a modified radius, and all raised to the 1/2 power. The cheating that we're going to do, and I'm right at 2:45, so I'll just show you this one last thing, and then we'll wrap up. So the cheating that I'm going to do is, what is this R star thing? Well, R star is just described as 1 over R star is equal to 1 over R1 plus 1 over R2. That's the equation for R star in this Hertzian model that we're using. And remember, I don't have two cylinders that are pushed up against each other. I have a cylinder that's pushed up against something that's flat. So if I make this radius R2 infinite, this cylinder basically just gets bigger and bigger and bigger and bigger and bigger. And the region very, very local to the smaller cylinder, from the small cylinder's perspective, essentially looks flat, right? So what I'm going to do is I'm going to say 1 over R star is just equal to 1 over R1 plus 1 over R2, but R2 is infinity. 1 over infinity goes to 0. And so R star in our case is just equal to R1, R subscript 1. And this is now for a cylinder getting compressed against a flat surface. So that will go into this pressure equation, and I'll solve this pressure equation ultimately to get the things that I need to plug in here to figure out what the pressure is in that gap area. But I am at the end of my time, so we'll stop there. Can I answer any kind of general questions before we stop recording?
What is a superscript next to the Young's modulus?
This guy?
Yeah, I can see what that is.
It's a star. It's like an asterisk.
Oh, okay, thank you.
Yeah, and that's just to let you know, right? If you guys remember back to your fluid mechanics class, when you non-dimensionalize a number, it's called like, modified velocity or modified length or whatever. You usually denote a modified variable with a star, and when I say modified, it's just like I did here, right? This has the units of radius, but it's some sort of weird combination between the radius of the small cylinder and the big cylinder. And so it differentiates itself from the small cylinder and the big cylinder with the asterisk, with the star. So that's all that is. It just lets you know that there's another equation out there somewhere that defines that variable in terms of the other variables that you can measure or look up.
Do we use these modified variables because we're making the assumption that the contact area is going to be like a rectangle?
You use the modified variables because that's the form of the Hertzian contact equation.
Okay.
So in other words, like I could actually write this out in all of its glory, but instead of writing R star, I would put like a parentheses here, and then I would write 1 over R1 plus 1 over R2 in that spot. It's what my old chemistry professor used to call the law of conservation of chalk. I'm just trying to, write less stuff to keep things simple.
Got it. Thanks.